Hi, my name is Pankaj. I am a client partner at Infosys. There is a fundamental change which is happening in how the world produces, analyzes and consumes data. This is true across all industries, across all parts of the value chain, and is also true for manufacturing firms and shop floors. If you look at a century back, how Henry Ford actually brought in manufacturing 2.0, where there were assembly lines and they produced same colored, same type of cars every 30 seconds, and that was manufacturing 2.0. Now the source of competitive advantage has moved on since then, and it is about being able to digitize information that is sitting in the shop floors and being able to understand it and be able to consume it. This is especially a challenge on the shop floors because over a period of 30-40 years there's been a proliferation of the kinds of machines there are, and traditionally those machines have not talked to each other. So earlier this week I caught up with Sobel, who is an author of MTConnect. He teaches at UC Berkeley, and he's been trying to solve this problem by setting standards, which is MTConnect, and making sure those disparate pieces of information can be connected together, and there's value which is coming out of the shop floors as a consequence.
Welcome here. Tell us a little bit about the buzz around machine-to-machine big data and the Internet of Things, and keep hearing about all these things. Tell us a little bit about it.
Well, from our standpoint, we're looking at the shop floor. The shop floor for manufacturing is islands of automation, separate machine tools, devices, cells that are all operating independently. They're producing a lot of information, but I'd say right now, if you look at your average manufacturing enterprise, you're talking about maybe 1% of that information actually making it out of the shop. So most of it just dropped on the floor. There's tons of information. I mean, compared to something like the Internet of Things, where you're collecting information out of, let's say, a temperature sensor or something else, the amount of information a single machine produces on a single part is incredible. And the amount of information, if you're going to analyze that, and the amount of value you could derive out of that to be able to increase efficiencies, increase productivity, is also incredible. We've just started scratching that surface. If you go back in history, before either MTConnect existed, MTConnect is a standard for getting data off of machine tools. Before MTConnect, there was really no standard for that. Every machine tool had its own proprietary interface. If you wanted to talk to a machine, you had to learn that interface, license that interface, work with the machine tool builder to give you the specs and the information about how the machine tool is put together. Now with MTConnect, you can take an application, connect up to the machine tool, and you know what everything means because we have controlled the vocabulary. We know everything is called out specifically by the name of that thing. A position is a position. A load is a load. Everything is defined ahead of time. That way, at the application level, we can analyze the data and figure out what's happening on that machine and how it's impacting the process.
Tell us a little bit more about the data. What kind of data are these shop floors, these machines producing?
Well, internally the machine tools are producing a huge amount of information. Every single movement, every position, every load, the current going through the motors, everything is there. By the time you get to the external API, you're able to get positions, loads, feeds, speeds, overrides, PLC information, basically information about the operation of the machine, alarms, and controller state, things like whether it's executing, what part program is currently being executed, what tool is currently in the chuck, and so forth. So you have a lot of information coming out of the controller and the PLC. There's also additional information you can get by adding sensors to a machine tool. One of the things that we do at System Insights is we also develop sensor components, like a high-speed energy sensor that we've developed to be able to collect data at 100 samples per second about exactly how much energy at any point that machine is consuming. This allows us to figure out what an old machine is doing, a machine that doesn't have a controller with any kind of accessibility. We're also developing other sensor technologies around vibration and acoustics to be able to understand, is there signal out there? Signal that actually operators pick up to understand whether the machine is operating correctly or not.
And what could those companies do of the data? I mean, of course, one is they could potentially figure out if the machine is working fine or not. Is there something else they could do with the data as well?
Well, the end goal of all manufacturing companies is to make money, right? And the end goal is also to be able to improve the efficiency of making parts. So how can we take a part from a raw piece of material, a work piece, take it through the manufacturing process and get it out at the end with quality, high quality, high tolerances, high accuracy, and repeatability. How do we do this while maximizing utilization of all the resources on the line so that there's as little waste as possible? So from the standpoint of what can software do, it can help that process become more efficient. We can analyze at multiple different levels, from the part flow level all the way down to the individual device level. What's happening in that process? Where are the opportunities? So what we do is we analyze using big data technologies, using rule-based event processing, what is happening on that machine. We contextualize the data within the process. That's another important thing. You have to take a look at the manufacturing process, what's happening, and then within what's happening, then what are the different signals? Because when the machine is producing, you're going to get certain signal. When the machine is stopped, you're going to get certain signals. You need to analyze those and figure out, okay, when is the machine producing? When is it producing chips? Then what is happening while it's producing those chips? So with our technology, we're able to look at that and look at, how can we increase the performance of the machine? How can we reduce the amount of time the machine is down between parts, between setup and so forth, and call out all those times. And also why it's down when it malfunctions. A lot of time is down when the machine simply is not working.
What you mentioned about is actually, I think that's very interesting, because that talks a lot about efficiency improvements, which are fairly important for manufacturing companies, where at times the margins could potentially be very low. What we've also seen is a lot of our clients, they are actually now increasingly looking at their manufacturing quality as a source of competitive advantage. Mm-hmm. And I believe a lot of that information could potentially also be used to produce that competitive advantage. What do you see in the industry?
I think efficiency, and I think quality, and I think productivity they're all competitive advantages. You can increase your margin, increase the accuracy, and the amount of tolerances that you can hold. I mean, one thing that American manufacturers look at, what differentiates America with a lot of other countries, is our ability to produce high quality, high accuracy parts. That's why we're top in some of the really high tech areas like medical and aerospace, which require incredibly complex processes. America has done incredibly well in these areas and still is leader in many of them, compared to countries that can produce high volumes, but not high volumes at that level of tolerance. Predictive technologies. If you look at big data analytics and shop floor analytics, what we need to get to, what we're moving towards, especially with some of the technologies that we're developing, are the predictive side of it. So when you're looking at a quality issue or some defect that occurs down the line, what led up to that? How do you trace that back to the individual processes where that defect was introduced? And then how do you find what was indicative of that defect? So in other words, you're getting all this information out of the machine, so you're getting loads, speeds, feeds, you're getting various tooling information. What's there that signals that that defect was now being made, or being introduced into that part? And then how do we correct it? And better yet, how do we eliminate that defect, or at least remove that part from the production process before it impacts all the rest of the processes down the line? So again, it's adding more value and not a loss that is going to happen at the end, but something that you can flag as being high probability of loss. How do you increase the probability that you're going to be able to reject parts up front in the manufacturing process?
How do you see manufacturing industry in the US 10 years from now? How different would it be vis-a-vis now?
In 10 years, I see that we're going to be there's going to be leadership in a couple different areas. The first area that I see is additive. I think right now, additive is an interesting technology. I don't see it as adding a lot to the industry for a little while. Mainly, there's a cost, there's a time. The additive equipment that we have right now is pretty slow relative to a standard forging with machining type process. So people I've talked to in this area have said that it's a really incredible technology, but it needs to go through some more iterations. And there's the material quality issues, crystal structure and so forth. It's not really my area, but I've been told by people who know what they're talking about that there's still some issues that need to be resolved. These are being resolved. I mean, there's a lot of research going on, especially in Youngstown right now, around this area. So that's one area. So we have additive, which is going to be able to allow us to make shapes and especially internal structure of parts that we just can't do, can't even imagine right now. That's one area. The second area is a much more data-driven environment. So right now, processes are mainly, I would say for the most part, we're still at the clipboard level, as you said before. We are waiting for this, manufacturing 3.0. We're waiting for these new technologies to be able to really take hold, for people to start getting away from the paper-based systems on the shop and getting to fully integrated systems. The other thing that we're going to get into is more automation. We're doing a few research projects right now with NCDMM and a couple of other companies, and NIST as well, SWRI. The automation right now, as I see it, is a very cumbersome process. If you look at automation in the US, or actually most any place, the robot's going to cost you, let's say, 50 grand. To automate that robot will cost you somewhere between $150,000 to $200,000. So we're talking about a 2 to 4x multiplier on top of the cost of that piece of equipment. Shouldn't be that. It's also the cost of programming that robot is very high. It's all teach-based now. There are some projects like Ross Industrial, which we're working with right now, that has a more programmatic methodology of going at it. You tell the robot, here's my environment, this is my collision domain, I want to go from point A to point B, the robot figures it out. Technology's there. We can also automate the integration with the machine tools, the CMMs, the conveyors, all the rest of those devices in that cell, and make it seamless, and make it software driven, so you can plug and play. If I want to put a CMM in my cell, it shouldn't take me 6 months. It shouldn't cost me the same amount as setting up the cell in the first place. I should just be able to do it, put it in, tell it where the part needs to go after the machine tool, needs to go into the CMM, have the part identification, the part kind, be communicated between devices seamlessly as well. I was talking to somebody in metrology about this who does CMM development, and they were saying, right now, one of the big limitations is they can't change parts because they are limited to 2 bits, because it's 2 DIOs, it's hardwired. He said, how many parts can how many different part types could you handle, program names? I said, well, infinite. It's text, it's, we're talking about network communication here. We're not talking about 8 or 12 wires. We're talking about being able to actually send data, having those machines communicate. This is where machine-to-machine is interesting. We're talking about real machine-to-machine communication now. Being able to have machines talk about, this is what I'm doing, this is what I need, and having the other devices fulfill those requirements and orchestrate the movements, the flow, and everything else. The benefits as far as fault tolerance, changeover, are immense. So what I'm seeing is automation with much more fluidity, data-driven, so we can do the analytics on top of what's happening in the automated cell without somebody having to write it down. So predictive, we'll know when failures are going to happen before they happen, and maintenance can schedule to do repairs before we actually have downtimes. We get additive as part of these processes as well, that it's going to be worked into the whole part flow and the part manufacturing process. So, looking out 10 years, I think, the landscape is going to be very different. I think the job of the operator is also going to change. And the operator is going to become much more technical. They're going to be watching multiple machines, multiple cells, operations, and making sure that everything is happening correctly, that quality is held up, that the machines, that everything is operating smoothly.
Era of mass manufacturing to a segment of one, how does that impact the shop floor and the data that gets produced and consumed in the shop floor?
So we talk about data of one, or product, single products, customizability. This is a big thing in manufacturing right now. We have this idea that everybody wants their product, the color, the shape, they want it done the way they. I mean, Local Motors is a great example of that, where you can buy a car online and design it yourself and assemble parts that are manufactured all over the place. What does it take to be able to do that and do that efficiently and do that where we can actually make money at it as well? Some of what I was just talking about. You need to be able to have fast switchover. You need to be able to go from this process to this process. So in other words, if I have a bunch of material coming in and I have 5 different variations on design, let's say, how fast can I switch over between those variations? How fast can I validate that? I mean, a lot of processes right now, the reason, as you said in the beginning, comes in one color black, was because it's hard to switch a process midstream. Paint booths now can switch over. I was at a BMW plant where they can switch in like 4 seconds to a different color. And this kind of technology is there. But still, from like the manufacturing side, we still have a part flow, and maybe there's 4 parts, and still there's a setup time, a switchover time, and everything else. I think what this technology can bring us is to understand, first off, from that data collection and analysis point of view, what does it take to be able to switch over? What are the impediments from an automation standpoint? We can flow all that material through. So once we have a firm idea of how we can flow it through, how we can switch over quickly, I think that will make a big difference. The other thing is that you're seeing, some of these more sophisticated machine tools, especially some of the ones that we have in the U.S. and Japan, Germany, these kind of things, the mill turns and everything else. You can do a fast switchover because a machine is very capable of being able to do highly variated programs. Again, the whole problem is, how do you keep that process consistent, keep the product coming out with high quality, high repeatability, but have high variance? That's the issue that I see is going to be solved.